Recording in progress.
We have started with chapter 5 on the equilibrium constant, and in particular in the introduction we started out with the first law, and we went into the free energy, right? And using the expressions we had previously obtained, we arrived at the expressions for the Helmholtz energy and the Gibbs free energy. Okay. And we identified that in order to deal with reactions, we have to deal with varying number of compounds or particles, right? And the corresponding quantity is the chemical potential. And so we introduced this symbol mu for that. Now, we continue today by getting an explicit expression now for mu. Okay, so we can do that because everything goes back to first principles, and we can simply use the Mathieu bridge which you have seen on Tuesday. So mu free energy with respect to n, and now we use the Mathieu bridge, so we have to differentiate RT logarithm Q. And that is, of course, nothing else than minus RT dn logarithm. And now again, we make use of what we've seen before, namely the microscopic individual partition function of many particles of the same kind, right? Now, thanks to our dear friend Stirling, we can write the logarithm of these factorials as follows. And that's just n times logarithm q, and then the in the argument of the logarithm, the denominator, thanks to Stirling, then becomes n logarithm n plus n. Yeah. So all of this we do prior to differentiation, and now we can go ahead and differentiate, and then n log q, right? The q doesn't depend on n, so we only have logarithm q left for that. Then we have n log n. When we differentiate, we have to use the product rule. So once I have logarithm n minus n times the derivative of the logarithm n, which is 1 over n. And then at the end, I have n differentiated, I get 1. Okay. Now here's minus n over n plus 1. That cancels. And so you see we have minus RT logarithm Q over N. This is a chemical potential in terms of the partition function. Is this clear? Any questions on the steps? I can make this more convenient by multiplying with 1. Okay. So more conveniently, I can say mu is minus RT logarithm. And now I write Q divided by the volume times volume over N. And that second fraction using ideal gas law is also kBT over pressure. Okay. So then I have minus RT logarithm of QV times kBT plus RT logarithm of pressure. Okay. Of course, you will wonder now why we do that. You'll see it in a second. But now you see these are just simple transformations. I hope that's all clear. So we are making an ideal gas law assumption here, right? And we also, when going from the capital case Q to the small case Q, we assumed the indistinguishability and non-interacting particles, right? So again, ideal gas law. Now, why did we do these last steps? Consider now the standard conditions. Mu 0 for a standard pressure P0. Okay. This mu 0 is minus RT logarithm Q over V kBT plus RT logarithm P0. And if we now use that as a reference, and we want to describe how things change for a different pressure, we can subtract the standard mu. And then you see that the entire first term is the same. And you're left with RT logarithm of P over P0. Right? So this would tell you how the chemical potential looks like, or what I like even more is to write it like this. So your chemical potential is some reference chemical potential plus RT logarithm P over P0. And any questions? So this quantity you will see will be crucial for later on arriving at the expression for our equilibrium constant. Okay. So an equilibrium constant is not something you can understand without making use of the chemical potential. I'd like to move to subchapter 5.2 now, where we will deal with reactions. Yeah. Have in your classical thermodynamics course, have you dealt with reactions? You have. So let's just quickly revise the generic notation. We have some stoichiometric factor, mu A, for a component A reacting with some other stoichiometric factor in equilibrium to some product Y, also with stoichiometric factors and Z. Okay. Now, in order to measure the progress in the reaction, we introduce psi is the progress variable, right? And you can think of it as it's like time or percentage of product being produced, right? And that allows us to look at the number of particles A corresponding to number of particles at the beginning of the reaction. So when you start to mix the components, minus psi times nu A, right? So the amount of component A is decreasing. Similarly, for component B, and your products are growing. Right? So the general formula is n equals n0 plus some change in dn, where dn is simply nu times the progress variable psi. And this infinitesimally small change in dn we write as d psi, right? Now psi has the units of mole, right? And your stoichiometric factor is just a factor, right? Unitless. So regarding the units, right? From here, you have a derivative, right? So there's a fraction of energy over particle number. So the units are energy over particle number. So for example, kilojoules per mole. Okay, but this is changing moles, right? Now, the particle number n is extensive, just as length, right? So the units of a force are energy over length. Now we have energy over particle number, right? So it literally is a force, but rather in space, it is a force in particle number. And so your psi represents the progress internally in such a reaction, right? And it combines, it collects all the variations in the particle numbers of the various components in your reaction. And these components are weighted differently according to their stoichiometric factor. Okay, so then, of course, the first question you must ask yourself is what happens to the energy? Right? It's the energy that determines things. So with these notations, we can consider dg, and that would be minus s dt plus vdp plus all the chemical potentials times changes in particles. Okay, so these are the different components we are summing over now, right? Now, let's suppose that we are talking here about an isothermal, right? So you plunge your reaction in some thermostat that fixes T, and isobaric. You're not changing your pressure by jumping off a mountain or something while doing the reaction. Oh, this was actually the question, why people are so fond about isobaric conditions. So the reason for this is that is what your average lab, given some altitude and some temperature, some weather, your pressure is fixed. And so you don't have to do anything else. If by contrast you need to fix your volume, you need to invest in a bomb calorimeter. I don't know if you've ever seen such devices. They are very heavy, very thick steel, and it's very complicated to do experiments in this thing. So way more convenient to be operating in the isobaric regime. Particular when it comes also to industrial scale chemistry. All right, so we set these first two terms to 0, right? And so under these conditions, you now notice what is driving your reaction, right? The energy is literally the chemical potential. There's nothing else left, okay? Now, these chemical potentials we can conveniently separate by summing over our products. And subtracting the sum over our reactants. Right? And I'm now replacing dNi by this definition, right? Our progress variable. Now we have our progress variable present and it's independent of the components. So I can also write this as my sum over Z mu C nu C minus my sum over A mu A nu A times D psi. Yeah. And again, this is our total differential G. And we are expressing now how G changes in progress of the reaction. Right? So in front, you have dG d psi. Right? That's your chemical force of the free energy for any reaction. Okay. This is so cool that people call this delta RG. Right? And this is, in words, the change in Gibbs energy per mole, right? Typically in kilojoule per mole. Now, this is clearly not a function of the path, right? Since G is a state function. So it doesn't really matter what happens in between your reactants and your products. And if you consider a reaction profile. G, the function of psi. You now have the reactants. And the product. And you have a change in the free energy of the reaction. Okay. Now, you probably already know that the kinetics is determined by the height of the barrier in between, but the thermodynamics is not. And equilibrium constant is not. And that's what we are after here. If you have a reaction with the same free energy difference and a huge barrier, it will have the same equilibrium constant. But it will happen on a different time scale, right? So there's a famous example for this. Consider graphite and diamond. Diamond is less stable than graphite, even though some people claim it's your best friend. And the reason it doesn't decompose spontaneously is that the barrier is so high that you would have to wait for spontaneous transformation for a very, very long time. But the equilibrium constant is very clear, right? Now, tragically, again, next week, you will have to live a little bit without me. On Tuesday, I will still be at the American Chemical Society meeting in San Diego. And the postdoc who already taught you was so kind to agree to explain you next Tuesday how we can actually find these barriers and the barrier heights. So that will be a little excursion again on Tuesday. To continue here, what you see now is that delta Rg is a function of stoichiometry. If the explicit dependency on your stoichiometric factors on the chemical composition of your substance, okay? Now, that, of course, begets the question, what happens to delta Rg as you consider other compositions? Right? And this is what this theoretical framework offers you to do, right? Because you can query this function again for a different composition. And then you can predict which reactant is going to be more favorable for a reaction and which one is less favorable. We can now continue with our delta Rg. And let me write it out once more. So products and reactants. And we now make use of our chemical potential. And in particular, this pressure now is referring to the pressure of the component we are looking at, right? So this is for some component I, and this is also known as partial pressure. Which I believe you've encountered as well. Now, insertion gives us sum over z nu c mu 0 c plus rt logarithm pc over p0 minus sum over a mu 0a plus rt logarithm pa p0. Now let's collect the mu 0 terms. And we have mu z nu c mu 0 z minus a nu a mu 0a, and this is the delta r g0. And then we have the interesting parts, rt sum over z nu c logarithm pz p0 minus sum over a nu a logarithm pa of p0. Now, remember, if you have something like this, that's the same as logarithm sum of logarithm x to the n. That's the same as logarithm the product of x to the n, right? So what you have now for your delta rg is your delta rg0 on the standard conditions plus rt logarithm product over z pz over p0 to the nu z. And that's for the products. And because of the logarithm, I'm pulling in my reactants with partial pressures. Okay. Everybody with me? Some questions? All clear? All right. So maybe you see already what we are after. right? Remember how in the equilibrium constant, your concentrations, they get exponentiated by the stoichiometric factors, right? You see this already here, right? You also see the fraction and the logarithm, right? But now you've seen maybe for the first time where this is actually coming from. Now, how do we get to our equation we were originally looking for? Well, we say in the equilibrium, dg must be 0, right? So, in other words, your delta Rg is 0. And hence, delta Rg0 equals minus RT, the logarithm of this thing. Yeah. And with one more step, we can change this to concentrations if you consider the ideal gas. P equals N over V RT. N over V is a concentration, right? So concentration times RT. And then if you have the ratio of some reactant pressure over, so product pressure over reactant pressure, this simply becomes the ratio. The RT cancels and it becomes the ratio of the concentrations. And hence, your delta Rg0 equals minus RT logarithm K. So there's maybe an example to illustrate the power of the stoichiometrical factors in your chemical potential. Could be the Haber-Bosch procedure, which famously transforms nitrogen into ammonia. Now, one of the reasons why your delta G doesn't like that is that the stoichiometry is working against you, right? So ammonia is, of course, the starting material for fertilizers. It's a hugely important process for agriculture, for feeding the world, and a considerable amount of energy is dispensed every year in order to make this process happen. Because this runs against the free energy. And it's obvious why that's a tough one, because your partial pressure gets squared here, and you have in the denominator a cube times the pressure. So it's the individual gases are vastly reduced, right? The number of them, the stoichiometric factors. And so this is a very much an uphill battle. So you see also that these stoichiometric factors really explicitly enter your chemical potential, and they do that exponentially. Right? So it can be that these stoichiometric factors play a more important role than the actual nuclear charges and geometries your compounds are exhibiting. Right? Now, we also should note that we can directly measure delta Rg via concentration or partial pressures. In other words, given this theoretical framework and given the existence of a scale or pressure gauge, you should be able to calculate for standard conditions the corresponding free energy difference. Okay. Are there any more questions? So I'm done with this chapter 5.2. The next chapter 5.3 will look a little bit more explicitly again at the link to our partition function. And I'd like to do that in 1 week. And that should allow us also to discuss intuitive interpretation of equilibrium constants in terms of spectrum, the spectra of the states of reactant and products, right? So the partition function is really the link between the solutions of Schrödinger's equations, and you have those solutions for reactants and for products. And so we will see from the positioning of the spectra and from the density of the spectra, we can then intuitively predict if the free energy change will be positive or negative, right? So which state would be preferred. I'd like to thank you for your attention, and I wish you a nice weekend.